Welcome to Alpha Beta Tutorials. In this video, I'm going to solve another West African Senior School Certificate Examination Physics Practical. The aim of this experiment is to determine the acceleration due to gravity on Earth using a simple pendulum. Let's get started. You are provided with a meter rule, a pendulum bulb. We don't have a split cork, so we'll replace it with this. A stopwatch, inextensible string, and a retort stand. Observation on measuring instruments. The least count of the meter rule is 0.1 centimeters. That is the smallest length the meter rule can measure. And also, if the length is recorded in centimeters, it should be in 1 decimal place. That's the meaning. And the least count of the stopwatch is 0.01 seconds. That means the smallest time the stopwatch can measure is 0.01 seconds. And also the time should be in 2 decimal places. Set up the apparatus as shown in the diagram. So we have the retort stand here, and this is the split cork and the inextensible string here, and then the pendulum bulb is here. Measure and record the distance L is equal to 90 centimeters from the center of the bulb to the point of suspension of the pendulum. So we measure a distance of 90 centimeters from the base of the split cork to the center of the pendulum bulb. We are going to displace the pendulum bulb through a small angle and release it, and allow the pendulum to attain free oscillations, and determine the time for 20 complete oscillations. When we release the bulb from this direction and it moves to this direction and comes back, it will be counted as one complete oscillation, and we are going to determine the time for 20 complete oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So the time 1 for 20 complete oscillations is 38.28 seconds. And we are going to determine the time for 20 complete oscillations again in order to reduce error. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So the time T2 for 20 complete oscillations is 38.18 seconds. So the length of the inextensible string is 90.0 centimeters. Remember, the least count of the meter rule is 0.1 centimeters. That means all the values falling under the length should be in one decimal place. So we have 90.0 centimeters. But we have to convert the length to meters. That is the SI unit of length. So 90 divided by 100 will be 0.9. But the least count is 0.1. When we divide 0.1 by 100, we have 0.001. That is 3 decimal places. So the length should be in 3 decimal places. The length in meters should be in 3 decimal places. This is the time 1 in seconds, time 2 also in seconds. The unit should be written here at the top once, and it shouldn't be repeated with the values. Then we find the mean of the 2 times. That will be 38.28 plus 38.18 divided by 2. That is 38.23 seconds. Then we determine the period of oscillations and evaluate the period squared. We have the period in seconds. The period is the time for one complete oscillation, and the mean time is the time for 20 complete oscillations. So when we divide the mean time or the average time by 20, we have the period. So 38.23 divided by 20 will give us 1.91, and we square the period, and the unit will be seconds squared. So 1.91 squared is 3.65. Then we repeat the procedure for 4 other values of length is equal to 80 centimeters, 70 centimeters, 60 centimeters, and 50 centimeters. So we change the length of the inextensible string to 80 centimeters, that is 0.8 meters, but we leave it in 3 decimal places. Record the time for 20 complete oscillations. Repeat the time. Find the average of the 2 times. Determine the period and evaluate the period squared. Repeat the procedure for 70 centimeters, 60 centimeters, 50 centimeters, and tabulate the results. So this is the table of values, and the numbers under each column should be in the same number of decimal place or places. For instance, the length in centimeters, the values are in 1 decimal place. The values in this column too are in 3 decimal places, and all of them are in 3 decimal places. And the values here are in 2 decimal places. The values here 2 decimal places, 2 decimal places. And we are going to plot a graph of t squared on the vertical axis and L on the horizontal axis, starting both axes from the origin. So for the values of t squared, we have 3.65, and it will be difficult to plot 3.65 on the graph. So we move this point 1, 2, and record it as 365 and times 10 exponent negative 2, and the unit is second square. So it's in standard form. So the value 365 is times 10 exponent negative 2, which gives back 3.65. For the next value, we move the point 1, 2, and we have 324. The next value 282, 243, and 202. So all the values are in standard form. That means each value is multiplied by 10 exponent negative 2 to give the value here. And for the values of L in meters, we move the point 1, 2, we have 90, also times 10 exponent negative 2, and the unit is meters. The next value, we move the point 1, 2, we have 80, the next one is 70, 60, and 50, all times 10 exponent negative 2 in meters. So we draw the vertical and horizontal axis. We are plotting a graph of t squared on the vertical axis and L on the horizontal axis. We choose a scale. We will choose a scale of 2 centimeters is to 50 times 10 exponent negative 2 second square on t squared axis. So we start from 0, 50, 100, 150, 200, and so on. And on the L axis, we choose a scale of 2 centimeters to 10 meters. So from 0, we have 10, 20, 30, 40, 50, and so on. On this axis, 50 divided by 10 is 5. So one small box on the vertical axis is 5. And on this axis too, we have 10 divided by 10, so one small box on the horizontal axis is 1. Okay, so for the first point, we have 90 on the horizontal axis, 365 on the vertical axis. So we have 90 here. This is 350. One box is 5. So 355, 360, 365. That is 3 boxes. And the second point, we have 80 on the horizontal axis and 324 on the vertical axis. So this is 300. One box is 5, so 300 and 5, 10, 15, 20, and the 4 will be in the next box. The next point, we have 70 on the horizontal axis, 282 on the vertical. This is 200. This is 250. So 255, 260, 65, 70, 75, 80, 82 will be in the next box. The next one is 60 and 243. This is 200. The middle will be 225, 230, 235, 240, 243 will be in the next box. The last one will have 50 and This is 200, and then 2 will enter into the next box. So we draw the line of best fit. Determine the slope S of the graph. So we draw a horizontal and a vertical line. We name here A, B, and C. The slope is change in BC over change in AB. For change in BC, we have 305, 10, 15, 20. 320 minus 200 times 10 exponent negative 2, and the unit is second square. For change in AB, we have 80 minus 50, also times 10 exponent negative 2, and the unit is meters. So times 10 exponent negative 2 will cancel out, and 320 minus 200 is 120. The unit is second square. 80 minus 50 is 30 meters. And 120 divided by 30 is 4. At the numerator, we have second square, and the reciprocal of meters is per meters. Evaluate P is equal to 4 pi squared divided by the slope. Pi is 3.142, and the slope is 4 second square per meter, so we replace them. 4 will cancel out. The only value left is 3.142 squared, which is 9.87. And for the units, they are all at the denominator. So the reciprocal of per meters is meters, and the reciprocal of second squared is per second squared. This value represents the acceleration due to gravity on Earth. 9.87 meters per second squared.